Well, hi, good morning. Thanks so much for joining me here in my shop. We're just looking out my front window at the snowfall from yesterday, along with my cat Shadow right in the window there. So once I'm done in the shop here, I'll be out there with my snowblower clearing out my driveway. So, great. So it took me about an hour to get that camera to work on there. Here it is, here on my phone too. So that's where I've been the last hour. Just trying to get those IP cameras are complicated to get to work. So here we go. What are we doing here? We're going to look at these two very, very similar voltmeters that I have. And now I will admit to something. I never realized that these were essentially very, very similar meters. Believe it or not, they're here in my shop. They're looking at me all the time. I never recognized the similarity. This is they're both Heathkit, and I'm pretty sure they were built as kits by somebody, and I've acquired them since then. I don't think they were built, I don't think they were owned by the same person. I think they've come to me in two tracks and ended up here. So this is a Heathkit model IM-11, and this is the Heathkit model IM-13. But I'm going to guess, electronically, they're extremely similar. One thing I noticed right away are these calibration access holes for putting in a calibrating tool. I don't see... Now that's probably the sound of the handle rolling around inside. It's been my practice to remove the handles when I need to, and then to store them inside the unit so they won't be lost. Shouldn't be wandering around. So both these guys use the very same kind of cord here in that it works from this kind of plug. And this is actually, you know, when I look at this, I think I've got one that's built more appropriately. It has a much larger insulator here, so you could put a more substantial voltage across here. This really isn't built for voltage. So the history of these, I don't really know. Okay, I don't know. This is my own positive connection, or you know, this is the ground side. This is let's call it the positive side on here. This is not appropriate for DC work. I should have a different probe, and somewhere I have an appropriate probe, which I'm going to get out, and we're going to see about making all this stuff work properly. So the special probe that's missing, I believe all it amounts to is a resistor at the far end here, which reduces the amount of current being drawn by the meter. I think that's the idea. Isolates the meter a little more from the item under test. Not 100% sure about that. So that's where we're going with this. I think one of the first things we want to do is examine the case voltages. My last video I posted was me fooling around with case voltages on these other pieces of equipment. These guys are in the same boat. The boat of equipment with the non-polarized two-prong plugs out of the 50s and 60s and maybe the early 70s too, before they began to polarize these plugs. Where's the other plug here? Here it is here. So the challenge is to get these guys plugged into the wall in such a way that the case voltage is minimal relative to the power system neutral in my house and to each other. So we have them both in the good way, and not one in the good way and one in the bad way. Now if you watched the video I last posted, the good way depends upon whether the units are switched on or off. So, and we are talking about voltages here that on a high impedance meter show up, sometimes as much as pretty much full line voltage. But even though they're able to make the meter like this read those high voltages, they kind of, well, there isn't very much charge behind them. So you could draw, you could touch something like that, draw away the charge. You can put it that way. So with the meter, read 100 volts. With your hand, 2 volts. That's kind of the deal. But what if it's not? What if there's a real problem in here, and when you touch it with your hand, you are now 120 volts? So that's the first thing we want to investigate here. So to do that, I'm going to bring up my now oh so cool box there. Why did I say it was cool? Because I learned on the last video that perhaps I've had an unfair attitude about some of these. I think these surge arresting things here are kind of a joke in a way, but wow, there's a significant electronics inside this guy. So let's check them out here. So we can only guess to start off with, and as I said, it depends upon how the switches are set here. Plug them both in. Make sure they're not in contact. Make sure they're both off. Okay. Power on. And I'm gonna need a voltmeter here. This guy. Let's use this one over here. We'll use this one. And I need a couple of leads. Just 1 second. Now, years ago, when I was actually living in another house with a different, similar but different shop, I was working away in my shop, over here, let's say, and suddenly there was a significant boom, spark blew out from between two pieces of equipment. I don't know which two it was now, like just out of here, let's say, out of this space here, boom, came shooting out. It was different shop, different arrangement, different everything. But I wasn't even touching the equipment. There was enough voltage between two cases that when they finally touched, there was quite a spark. So, you know, that kind of opened my eyes. That's why I'm sharing that with you. You don't get a big popping short from little currents flowing through leaky capacitors in here. That's not you're getting something right off the line. I was surprised my fuse didn't blow. That's how big a deal it was. Okay, we're ready here. We are ready here. So I really don't want to take responsibility for anyone else's safety but my own. Oops, I know on these videos there are people watching who are kind of learning this or just starting into it. What I'm trying to demonstrate here is just about the most important or basic safety issue that you need to resolve if you're going to fiddle around you're going to make a shop like mine and fiddle around in there. You need to understand what it is I'm doing, but I'm probably not going to explain it well enough. So here we are. I'm on the AC. The question is, how much voltage is there between these two cases? So 56, which is roughly, it's exactly half of 112. So that's a good sign, in fact. No, it isn't, Jim. Well, maybe it is. Let me switch one plug around. Just one here. And reverse it. What are we going to get? Okay, my guess is we will see the same voltage again. Maybe not. Let's see. It's a bad guess. Actually, I was going to guess no voltage, but I thought just for the interest's sake, I would guess the opposite. So what's happened here now are these two cases are at a similar voltage, but it doesn't mean they're safe. They're safe relative to each other. You're not going to feel 3 volts. At the moment, they're safe relative to each other. And conceivably, these are safe all the time, even with voltage between them, because the current flow is restricted through a capacitor, or maybe it's just transformer capacitance that's allowing this to happen. But let's check it now to a real ground. And where is a handy real ground? It's right here. Real ground, shame on me. What I should be saying is voltage to the hydro neutral. 84 volts. So what we will try now, again, I don't think there's much oomph behind these, but I'm not going to stick my fingers there to find out. If there was a lot of oomph, I think we would see 120 volts. That's what I think. Because if there isn't enough oomph to push this meter all the way over. Kind of look at it that way. Kind of. So now I would expect to find the same 3 volts here. Even a little bit less. And when I check the ground, okay, anybody got a guess? What's it going to say? Notice I didn't even say anything. So now I have selected the most appropriate way to have this equipment plugged in. When it's switched off, let's turn it on now. We'll turn one on. Remember, voltage between them at the moment is, look at that. I mean, that's as good as zero. Switch one on. Now what do you get? Ta 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 ta. 100 volts. Now if I want to get rid of this 100 volts, I'm going to have to turn on the other one. Now what do we get? Well, it's not 120, but it's still pretty high. So this is the thing about these guys, these meters. These little voltages exist. And as I tried to demonstrate yesterday, even if there's no real shock or fire or big short circuit type issue, there can be noise issues from these. Just from the slight currents that, and I have nothing on in the shop that we can hear this noise, but that is probably causing a little bit of electrical noise. The other thing too is if you're not careful, these case voltages, which in the case of these two guys, this is not insulated away. The case voltage ends up right on here. Is that true? Make these statements, I better check it. So we should see 0 voltage here. 0. Now that's a little different than some of these other instruments here. These guys, this one with terminals. Let's go over a little bit further. Well, you can't see it in the dark here too well, but it's got the 3 terminals down here on the capacitor checker. Those terminals are insulated away from the case. These are things you got to make observation of. You got to look for this stuff and kind of see what you're dealing with. Because, as I've said before, maintaining your safety in a situation like this is about knowing what you're doing and trying not to get killed on the way to finding out. That's kind of it. Now, what are the chances of getting killed in here? The odds are extremely low. If they were at all high, I wouldn't be here. I'm not looking to get killed. So yes, there is a chance you could electrocute yourself in here, but with a little bit of electrical knowledge and a little bit of good practice, chances actually go pretty low. How do most people get electrocuted? Well, I'm not sure there's any one thing that really stands out, but one thing I can think of is the electric lawnmower with the bare hands on the metal and either bare feet or, God help you, bare feet with a lawnmower, or lousy running shoes, walking in wet grass. That's a real danger. Bad extension cord, maybe the green wire is broken or you've cut it away because you're dumb or something like that. People get killed with lawnmowers. People really do die at 120 volts. It really does happen. Now that I'm scared the living bejesus out of myself, and in the city of Toronto, you probably have 1, 2, or 3 electrocution deaths a year, something of that sort. Not sure why my meter's doing its own thing over there. Looks like it's heavily damped, and it's responding literally to the AC voltage that's here. So it just looks like it's damped. It's moving very slowly. Okay, back to what we were doing. What were we doing? We were talking about these leads. We're checking to make sure this was really connected to the case, which it is. So let's compare the accuracy of these two meters. We'll start with this one. We're on the AC scale. I'm going to want to read, let's say, the voltage coming out of here. Okay. I'll do that with my oh so dangerous cable here. Power's off at the moment. I'm plugging into an isolation transformer. It has no relationship to ground. Doesn't matter which one of these I put the ground on. I closed my eyes when I did that, by the way. So we're getting a reading already, but it's bogus. So we're on AC, 150 volt scale. So now give it the juice. So without any calibration or anything being done, we can be pretty sure the voltage is 123.6 volts. And on here, on the AC scale, 150 AC scale. It says AC/DC. Right, top scale then, no problem. 140 volts. Now let's check a couple things here. Now we have a before I get myself a shock. Shut that off. Separate these. Let's do this. That makes me feel much better. Okay. Short these together. Checking the zero. Zero adjust. Is it? Yeah. It does have an effect. Even in AC, it's definitely on zero. That's all I needed to do. So we're really getting a wrong reading of 140 on there. Okay, we'll go here. Try this guy. 150 volt scale, AC. Okay, hook this up first. Here, 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 and lastly here. 123.7 on here, and this is reading, also reading high. It'll be like 138. So both these meters would compare favorably, but they're not reading the right voltage. And what if we just take another closer look? You know what? I've almost got a short circuit right there. Come, son of a gun. Let's just fix that. That's really close, man. It's really close. I wasn't really looking. That's an interesting question now. What would happen? This is a good question for me to think about. What would happen if I shorted these out? I have these plugged into this, which is then plugged to an isolation transformer, which is then plugged into the wall. So the question would be, if I short these out, if I have a short circuit in my shop here, is that going to draw enough current through my isolation transformer to pop the circuit breaker open, my 15 amp circuit breaker, pop it open? And the answer is, gee, I don't know. That's a serious problem. Because if you did set up a short circuit, and assuming you didn't realize it, which I'm pretty sure you would realize it pretty quick, but if you didn't, the short circuit could persist. My circuit breaker won't open, so that fault will continue producing heat, and you're going to get a fire or something else like that. It's an interesting question, and I have no idea how I could test it other than to actually short that out and hit the power, which I'm not going to do, but it's something to keep in mind anyway. When I use my dim lights in here, the dim light bulbs, of course there's no chance of that happening, because a total short circuit here would simply turn the lights on over there. So good thinking. Let's energize it with the dim lights. Okay, and we're going to read the voltage here and compare it to everything, including this. 123.9 is what it says on there. It's really darn close, isn't it? Okay, it still says 123. It's bopping around between 0.7 and 0.9. So it's basically 123.9, 124.3. And both meters could be correct? No. I'm reading a higher voltage past this meter. So one of these guys is not 100%. So in the meantime, this one is still reading 139 little sticky there. China syndrome. Oh no. Any other? Well, let's try this. Okay, so this goes up to 1500. This goes up to 1500. Let's try the same measurement at 1500. The scale 1500. So 1500 would be this 1500. So we're going to see it really barely come up. This isn't zeroed. This is not zeroed. Okay, now it is zeroed. $150. Oh, for crying out loud. I'm holding these. It's like typing on the wrong keyboard. I'm holding these leads. I'm looking at that meter. So now on the 150 volt scale, we're right over 150 volts. So both these meters are reading substantially high. On the 1500 scale, oh, you know what I did? I zeroed it with a... you did know what I did. It's just that I don't know what I did. Okay, let's take this off. Duh. What a bozo. Let's zero it up. Hey, it's all part of learning, right? Try it again. Careful now, don't get a shock. Hard to see. 1500 scale. I would read about 165, something like that. Now, I dare pull this out. Pull this out with the leads connected. I think that's a no. I think that's a big no-no on this machine, especially since I know this plug here is not quite the right one. Let's stick her in. Yeah, the next thing we'll do after this is I'll locate the probe, which I haven't seen for quite a while. I will try to find the probe, proper DC probe. Put this on here, don't get a shock. Lots of leads on the table here. Okay, what do we got on here? So on the 1500 scale, we're way down, we're just over 100 here, about 120. It's really 123. Very accurately. Yeah, you know what? That could be 123. Right on. Go back. 500 volt scale. Now we're reading 150 volts, and the 150 volt scale, 140 volts, and the 50 volt scale we won't try for obvious reasons. Let me cut the power. So I'm going to try to find. Cut the power and everything. Oh, don't be fooled, Jim. You've cut the power to this. You didn't cut the power to the. Yeah, these two guys are just basically plugged in the wall. Let me get this danger thing out of here. Okay. Yeah, because I want to end up with proper leads and everything, even if I have to manufacture my own new leads for these guys. So I'm going to go look for that other thing. It wasn't too difficult to find the proper probe. Here it is. And it has a switch on it, DC, AC, and ohms, I believe is how this works. Now, the reason I don't use this is kind of simple. I don't have an easily accessible ground wire coming off it. That's the only reason I don't use this. And I don't appreciate the value of having a resistor up here or whatever's going on in here. So I think by the end of this little deal, I will much more appreciate the value of this probe. This will probably be what I start using, in fact. And you can see the difference in the plug here. This one's not appropriate. This one is appropriate. This is a large insulator there. This is the only plug I've got like this. All the rest are just like that. But I think this would only become critical if you're testing 600 or 1000 volts or something like that. I'm not about to do that, as far as I know. So I'm setting up here so we can compare a couple voltage readings. I don't think we're going to learn anything dramatic here. So I'll take the this out of the way. So I have a DC power supply up here, which we're going to turn on. I'll be able to raise the voltage to a couple hundred volts or something like that. The voltage is going to appear right down here on these clip leads, which I clipped to a piece of cardboard just to make sure they don't touch each other. Piece of wood, actually. Piece of wood. So we'll put this on 150, and first we'll set 150 volts on here according to the meters up here. Okay, so on. We'll crank it up to 150. So that's on this meter, but you know, there's no accuracy there. So it's 150 volts now. 150 real Hertz volts on the end of these leads here. Don't think there's an issue with the ground connection. There's a two-prong plug, no feed through this device back to the power neutral, unless something funny's been done to it. So we shouldn't really be able to get a short circuit of that type. Put this on here. These are all famous last words you're hearing me say. Any one of them at any time. Okay, so we're going to put this on DC because we're smart enough to do that. 150 volt scale. This should come right up to there and stop. So I see 140 there. But dead on 140. Okay, we're going to disconnect from there. We're going to switch test leads. I believe the concept here is the resistor in the end of that probe. Where did they put it? I've lost it. I put it somewhere for safekeeping briefly. Now, son of a gun, it's right here. I'm looking all over the place for it. Here we are. Plug this one in. Now, difficulty, I do not have a ground lead. There's no ground terminal here to bring an extra lead out. This is exactly why I stopped using this. So I'm going to put a clip from a little bit of bare wire here down to one of these. That'll serve as the, I hate to use the term negative return. Okay, I'll put that there. Probe is switched to DC. Do we see 140? Scare the heck out of me like that. So I see 130, 128 or so. Let's flip this to AC. There's the whole 140. So no question, we're engaging a resistor here. I have a big problem with this. How do you get an accurate reading unless this meter's calibrated for this resistor? Apparently not, because we know there's 140 volts there. How do we know that? How do we know that? We know that because we have a reliable, trustworthy meter here, and we can double check. What just happened? Oh, it's DC. It's DC. DC. Take your time, Jim. This high voltage stuff you're doing here. So 138, almost exactly 140. That bodes really well for this meter not using this resistor deal here. So I'm not exactly where I've been all my life with this thing. I think it ruins the readings, and I don't understand how to use it because I've never availed myself, because I've never had one that was usable. I've always anyway. So I'm going to sort all that out once and for all, for my own sake. Let's disconnect this. Hey, let's use the other meter now. Okay, so remember, high voltage, Jim, don't forget that. That's a Hertz voltage there. There is enough behind this to really give you a lift. Now, I have gotten high DC voltage shocks. When you get an AC shock out of an outlet, you can feel the 60 cycles, right? I mean, the shock hums. Mm-hmm. But when you get it off DC, there's no hum. It's just a shock. So first, so we've got this probe hooked up. So we'll go ahead with this one now. Put this on 150. There we are. So we're on the 150 scale, expecting to see 140 volts on here. First, we'll flip to AC. The assumption is now it's straight through. What do we get? Ooh, what happened there? Oh, AC. That's what happened there. Da. I even confirmed my error. Okay, here we go. The zero's way off. That swung right over to just under 150. Now we'll flip it to DC. 140. So we lost what, 8%, 7% of the voltage is lost. So in my mind, what's going on here, and we're going to find out if this is really true. There's a 1 million ohm resistor in here, and this is a 10 million ohm impedance input. By sticking a 1 million ohm resistor here, you're creating a voltage divider. You're taking off about 10% of this supplied voltage. You're dropping it on this resistor up here. Okay. Reasons for that? I don't have a firm grip on it. I want to get there. Another thing I would like to work out this time around too is getting an RF probe together. I've been told too many times I really need an RF probe. I tried one or two in here. Hasn't worked out at all. So I may get around to that too. So what are we discovering here? We're discovering these meters are relatively accurate. They seem to be working fairly okay. It has case voltage issues. Ultimately, I'm pretty sure now what I'm going to do in my shop once I finish restoring this stuff is run a common bus between them to eliminate this case voltage under all circumstances. And if by some chance with that negative or ground bus running through, if somehow I should accidentally energize the bus, then with any luck my circuit breaker will pop open. I'll be safe. Anyway, that's my thinking on that. Next step, I think, is I'll use checking the resistance readings. They're based on batteries that are or are not inside these. Next step is take the case off and do a general inspection of what's inside them, inside these two units, and then plan out. And what the next step is to turn off the high voltage. That's really the next step. Pull these out of here. That's really what I should have done immediately upon finishing that test. Good though. So that's what I'll do. I'll take these cases off. Let's kill the power. Pull the plugs. So every time I pull these plugs out, when I go to plug them back in, I have to go through some kind of resolution testing here, or I've got to mark these, which would probably be a smart idea. Probably be smart. Next time around, I'm going to mark them. I will mark them. Hey, I just thought of an experiment. Yeah, let's try this. Let's try this little test here. So we're got the plug to this unit. I'm going to go here. I'm going to go here. So, and what am I hooking it up to? Absolutely nothing. Let's use this meter here. Resistance measurement. Well, I think it's saying it's open circuit. Am I using the right unit here? Yeah. I'm a little surprised at that. I kind of thought we would see something. It's a megohms. That's pretty reassuring. So I'm just looking for a leak, basically, between the power transformer primary, which is where the wait a minute. This is switched on, so we're okay. Yeah. The primary and the cabinet, and there appears to be nothing. So this means when I'm getting these low voltages, they may be traveling through a resistance that's, what, more than this meter can read? I'm not sure about that. So we'll check the other one now. Same way. Just put this on, yeah, same way, different plug. Onto the ground here. Oh, something happened there. I've been restoring my leads here faithfully every night. So leads are pretty reliable. So this gives the same reading. There certainly isn't any really significant short between the power transformer primary and the wiring associated with it and the cabinet and the cases. So and I didn't bring up my low impedance meter and prove that with a low impedance meter you don't see any of this stuff. So to some degree you're chasing ghosts. To some degree I am chasing ghosts. Okay, let's get the cabinets off here. Okay, here we are with the cabinets off, and sure enough, inside this was the old handle. Well, you know what? I hadn't really restrained it in there, which is kind of laying in there. It's not the best thing to have rattling around inside a meter like this. So now that they're apart and looking at them, you can really see the similarity in them. Anyway, let's flip them around. See what shows up on the other side. Okay, so some observations here right away. There's batteries in these guys. There's a battery right here. And Rayovac battery. Does it ever look old? And then there's one here, but I'm the guy who put this one in, I'm pretty sure. This is my battery here. The other thing that's leaping out already is a, these are not plugged in, is a great big diode here. Great big diode. Does not look original. This does not look original. The way it's soldered in, none of it looks original. I mean, it's just bopping there too. I don't want to touch it. It's just hanging here. Look at this. Oh my gosh, that's bad. Because the cabinet would be right here. Let's go bump into the cabinet. Did I do that? I don't remember doing that. What else do I see? I see an orange wire down here that's connected from somewhere around onto a lead of another resistor. You know, any wire connections to leads, that usually indicates something's gone on, because the normal thing is you don't tie one component to the lead of another. Let's get the close-up camera going on this stuff here. Bring her right in. Okay, we'll see if the autofocus can handle the situation here, but it probably can't. So what we're looking for are burned out parts or things that I might want to replace, and for sure that 20 microfarad capacitors. Top of the list. There's another molded capacitor back there, a white one you can see. Appears to be in good shape, but that's how it appears. Looking for burned out resistors. They're common in these kinds of things. A lot of black wires. You just use black wire everywhere. We're looking at the resistors down low there. Yeah, everything looks pretty good. There's some tucked way up under here. You know, the meter works on all scales and all functions. Whether it's accurate or not is another question. So let's take a look at where its accuracy would be coming from. Oh, look at that. Wow. Okay, that's a heck of a nice looking capacitor there. Look how it's sealed on the end with what looks like epoxy to me. That looks like a pretty reliable capacitor. I think that's a capacitor. Looks like a really expensive one. And we check out these resistors here. And these aren't looking very cheap either. These are all probably high precision. Yeah, 1%. You can see the 1% right there. Again, these are commonly burned out in devices like this. But with this thing working on all scales, relatively okay. These are probably all okay. Not necessarily, but I don't think there's any open. Now, what about that big brown thing out here? This doesn't look quite as good. This one here. The color bands look off. And what has happened to this white band here? What is that? So this appears to be cooked. To me, this guy's been cooked. Can't even rely on the colors to determine its value. It's a different and a higher wattage resistor. Look, it's taking this wire. Oh, look where it's coming from. You just follow that wire. Follow that wire. It's to the battery. It's far-fetched it would be burned out if all it's doing is carrying battery power. And it appears to be what it's doing. So this would be related to the ohm reading scale. Well, maybe that's gold. Maybe that's white, brown, gold. We'll have to find it on the schematic to really know what's going on there. A little bit of a different angle on it here. See the back of the switches. Probably could use some cleaning. Look at that cluster of resistors down here. All clustered together, going to one terminal. See the ball bearings in this control here. This is one of the adjustments for calibrating the unit. This is the zero adjustment here. Just looking at each individual part as best I can. There's a better view of that big brown capacitor there. Can we read anything on it? I don't see anything. I think one of the first things we can do here is we can take out that battery. Get that battery out of here. Like I say, I think I'm the guy who put this one in. Now the unit, the unit warms up a little bit and so this battery gets warmed up a little bit. Looks okay. So, I've had this guy apart. I've had him open like this, but I have not done any part changes unless this is me. I don't think this is me. But that's a really large diode to put in there for a little 10-watt machine. Okay, let's look at the other unit. I'm just going to put this one over here. Let's get the battery out of here right away. So this does not, transistor battery. This does not look like anything new to me. This might be 30, 40 years old. Made in Canada. No sign of leakage. looking for a date on it, but there's, oh, maybe here. Rayovac Division Canada Limited. I really can't read what's written right in the seam there. I don't know. Is that an antique battery? Nice shape. Now, what about this guy? I think this is the first time I've looked in. So we could guess that this is essentially the same circuit as the other one. Looks like the same meter movement, didn't it? So similarities right away of this pack of resistors here. It looks exactly the same. And you can see that one there. It's another one of those same resistors. Look, it's got the two. Where'd he go? Just a little harder to see here. So now that looks like white, red, gold, gold. And is it on the same? So it attaches to a blue wire, which I can't trace easily. So we don't know for sure. But this is probably doing the same thing. Probably going to the battery. Why exactly it's there? Well, we'll probably figure it out when we look at the schematic. Okay, any burned up parts in there? So with any luck, I don't have to change any of these resistors, but that would be luck. Maybe in a VTVM, these resistors are not at as much risk as in a ordinary indicating meter. I don't see anything about them. They all look great. Let's take a look at the board here. Nice and clean. Here's that capacitor. There's a diode. Now that's probably what the original diode looked like in the other unit. The other diode in the other unit has a bunch of hardware for bolting it into a chassis or something. It's really, and you know, these are typical failure points in these units. Just looking at every resistor in there. Oh, it looks really good. Now you can look right in at the movement. Well, I think the treatment on both these is really quite similar. Get rid of that big yellow capacitor in both these units right off the bat. And 16 millifarads here, 20 microfarads rather, 16 microfarads here, 150 volts, and the other one is 20 150 volts. Easy for me to replace these. So that's the first order of the day. It looks like it's exactly the same circuit, just laid out differently. Then I think what we would do is we would check the calibration of it, and then if the calibration is way off, or there's some other behavioral thing that's way off that we can pick up, then I might be inclined to replace some parts. What's this? Yeah, see, that's stuff from inside the capacitor leaking out. Gotta go. Okay, I know what I'm doing, so I'm gonna get rid of those two. Well, I think maybe the best next stop is the schematic here and take a look at this. And the reason is I'm trying to find replacement capacitors here in my shop for this electrolytic capacitor here, and all I've got are big guys at 50 microfarads, and this is only 16 here, and on the other schematic it would show 20. And going from 16 to 50 is a huge change. So I wanted to look at the schematic and see what the ramifications are of doing that, and there are some ramifications. So we look at how they designed this here. It's quite simple. You have the power supply transformer, you have a high voltage winding here, you have a diode stuck in the leg, and a capacitor across the output. So a way to think about this is the moment you energize this, the moment you close the switch here, this thing will be producing full voltage, or trying its best to produce full voltage. There's no slow ramp up in this thing. There's nothing slow about it. So the moment you close the switch, bang, the output voltage from this transformer is sitting where? Well, you might think it's across the diode and across the capacitor, but really, initially, a capacitor, you can think of the capacitor as being a short circuit. So upon turn on, what this diode sees is that it is all alone across the windings of this transformer. Now, it's only going to perceive that for a moment, because charge will start filling up this capacitor, and then the whole effect will slow down. But initially, this guy sees a short circuit. So the question is, how long does it sustain this heavy flow initial charge into the capacitor? I would guess if we double the size of this, the flow will be about 4 times as long. That's my guess. Or the heating effect, which is really what we're interested in here. We're interested actually in 2 things. One is the reverse voltage on this guy, and the other one is the current flow and the heating effect from the heavy current flow going through it. So I'm guessing double the size, you get 4 times the current. I squared R for watts, you get 4 squared, 16 times the power. So just rough, I'm trying to answer the question, is this really worth worrying about? Should I just pop a 50 microfarad in there and hit the switch? So I really think what would happen is I would pop this diode right away. I think so. It's a big one in the one unit, and the other one's got a medium-sized one. So they can sustain a fair bit. Maybe that's why these are fairly substantial, and this could even be why one of them failed and has been replaced. Because every time you turn the unit on, you whack it by charging this capacitor up. So one way I can slow down the whack here is put a small value high wattage resistor right in here. It doesn't even have to be high wattage, really. So that would retard the charge rate into the capacitor. It wouldn't take many ohms to make a fairly substantial difference here. Maybe 50 ohms. But at the same time, let's see, we would either put it here, that's not so smart. I could put it right in this leg here. So if we put it in the leg here, then it's in the circuit and dropping voltage due to current flowing into the actual unit. Not a lot of current. If we put it here, it's interfering with the filtering capability of this. And if we put it here, it doesn't help one bit with the inrush current. Don't think we want to drop the voltage out here. How much would it drop it by? So you can see right across the power supply is these resistances, 10K, 10K, 27K. So it's 10, 20, that's 50. So there's 50K right across the power supply right from the start. 50K. So they're using a very unusual symbol here. Look over here for a minute. So this is the typical earth symbol. What's that? That looks like the chassis symbol with the little hash marks missing. It's all over the place. So I'm pretty sure that's what that means. Tied to chassis. And this is actually tied to what? What would this be connected to that would be so different? It's only a 2-pronged plug. Earth to what? Or maybe you're supposed to put an earth on that. An earth connection. And this is well, I don't know. I was going to say maybe this is just showing it's connected to the case. But no. This is connected to the case. I don't know. little bit confused about that. Anywhere else you see a ground terminal? No, just right here. Okay, so I'm not sure what's going on with that. Notice the 12 AU7 is fed with two 6 volts applied to both legs of the heater here. Pilot lamps running at 6 volts. What else is worth noting? So I have an amplifier here. Yeah, this is over my head. I don't exactly know what they're doing. Look, they've got the grid on this side, kind of grounded. What's coming? So I don't. I'm not going to be able to fathom exactly how this is working, but that's okay. I don't need to fathom it. So here's the string of resistors. Notice they're doing that same pattern we noticed in the capacitor checker. 999. So you add these numbers up. If you add them all up, you probably get 10 megohms. This last one is supposed to be 10, isn't it? Something similar going on? No, these are done differently. They aren't following that pattern. 99999 all the way down. Or I could say more generally XXX all the way down. Second range deck. Range rear deck. Range second deck. Deck. Ohms, DC. I don't know what they mean by deck. Function second deck. Front deck, rear half. So maybe the deck, what I would call a switch wafer, maybe they're calling it a deck on here. And we can see, well, they got this drawn like this. They have the dotted line showing there's a mechanical relationship between this and this. What's this? Connected to these words? Must be this. Must be both these. That's what they've done. They could have spared me by drawing two dotted lines up to it. Then they put the word rear deck in the middle where I would use the word wafer. So this is probably the same wafer front and back. Does it say front and back? Not that I see. Okay. So here's a zero adjust. You can kind of look at it, you can kind of tell that's what it's doing. There was another adjustment over here, AC balance. AC balance. So in this meter, the 11, this is the IM-11, these adjustments are hidden inside the case. You have to take the case off to do them, but on the other unit, these adjustments are available at the front panel. Here we are. Here's a bunch of them. DC calibration, AC calibration, ohms adjust. This is what I'm really interested in. Fiddling with these and seeing if I can get this meter to be quite accurate across its ranges. There's a bunch of 22s. 22, 22. Why would they put 4 spread out like that? Why wouldn't they just make one 88 higher wattage resistor? Why have they done this? Over to the DC AC balance control. Why would they do that? Somebody worked out it was cheaper to put 3 lower wattage resistors spread out than to put one higher wattage resistor. I don't know. I don't know what's going on there. Then its brother is stuffed over here. Another 22. Front half, what is this switch for? Don't know. What's this megohm doing here? Where's the probe? So this is somebody's website. These are some of the things he did with this unit. He put the battery into this case so it wouldn't leak into it. That's a pretty good idea. Put these 3 terminals on the front to get rid of the banana plug. And he stuck a megohm resistor, he's talking about it here, whoops, in the test lead terminal, the thing that's up in the actual probe. There's this finished unit, nice pointer, nice knobs on it. Look at these terminals you put in. this resistor probably would be better off right at the end of the terminal. That doesn't show. Oh, here we are. Here we are. This is the probe. Does it show up down here? No. Good. Okay, let's look at this. Why is there another schematic? Just a quick look around it. All looks the same. I don't know why they should have two schematics here. But here's the probe. Very simple. So in AC and ohms, the center conductor just goes right out to the probe point. Flip it to DC and you introduce a 1 meg resistor. That 1 meg resistor, oh, it's going to be hard to trace now. I wanted to see what kind of resistance the 1 meg was running into. Not going to be able to figure it out by looking at this. Could always measure it. We just measure. Just take an ohmmeter and measure back into the unit and see what it's facing. I only do that for interest's sake. Now, getting back to this real question of the capacitor. Pretty sure if I put a 50 microfarad in there, I'm going to pop this. Pretty sure of that. So I would like to put a resistor in here. Let's say we want to staunch the flow. What voltage is this? Does it say anywhere in here? Maybe it says somewhere in the unit. Well, let's guess. So this is driving the plate of a tube. Let's guess it's 200 volts. 200 volts, half wave rectified. Yeah, okay, so let's carry on with it. 200 volts. 200 volts pushing on, let's say, for easy calculation, 100 ohms. 200 volts on 100 ohms is going to give you 2 amps. 2 amp charge flowing through this. 2 amps, these guys can handle that kind of current. The big ones can handle that kind of current. The 100 ohms here. I put 100 ohms here now, and this unit is drawing, let's just take a guess, on the B plus line, 1, 2, 1, 2. Okay, let's say 20 milliamps. So we're drawing 20 milliamps. You're not really drawing it from here, but let's pretend we are drawing it from here. So I want to work out the voltage drop. So we put a 100 ohm resistor in here. You got 20 milliamps going through it. 20 milliamps would be the same as I make that a 1000 ohm resistor. Then the 200 milliamps. 0.2 what? I don't know. I've lost track of my calculation here. Yeah, 0.2. Let's try it again. I'm trying to work out the voltage drop here on the assumption of 20 milliamps flowing through a 100 ohm resistor. 20 milliamps through a 1000 ohm resistor gives you 20 volts, 2 volts. So we'd have 2 volt loss if all the current being supplied were coming through here. I'm not sure how to analyze this. It sounds like 100 ohms wouldn't hurt. Sounds like 100 ohms would prevent 2 amps. I mean, there's a time constant here. This thing could draw 10 amps for a fraction of a second, or even more, for an even smaller fraction of a second. Let's take a 100 ohm resistor in here, put in a 50. I do have capacitors on order, but they're not going to be here for another 5 weeks yet. And then I would have the appropriate ones, but I'm not going to wait. Why don't we try that? Now, what happens if I ruin the filtration here? Well, starting off, this is if they were worried about filtering this really seriously, they would have put a full wave rectifier into here, not a half wave. And the small capacitance and the lack of a resistor and everything else indicates that there's very little draw on this power supply, so they don't need much to get it smoothed out. All these things bode really well for me sticking a 50 in there with a 100 ohm resistor. 100 ohms with 120 volts across it is 1 amp. But it's not 120 volts, Jim. We're thinking it's 200. Could be quite a bit more. So what if it is quite a bit more? What if it's 300? So you have 300 volts across 100 ohms. It gives you 3 amps. It'd be 3 amps. I hope it's not that. We can measure it. We can measure this. We can look at the kind of problem that this is causing right now, hum-wise. We can measure the current flow in here. We can do all these things and figure it out before we stick a 50 in there, and worse yet, pop a winding open, which I think is very unlikely. But I don't, I'm not trying to break these things. Okay, let's do some tests. So we're going to want to plug them in. We'll stick on this unit. We'll cut our teeth on this unit here. Okay. The other thing, when I plug it in, I'm not going to plug it into this outlet anymore. I'm going to plug it into my bench supply outlet. Oh my gosh, I got it. Look what I just found. Man alive. Oh boy. Let's flip over to the close-up camera here. This might not work well on close-up either. This is the cord to the bigger unit. Yeah, that's copper. That's a solder strike, and look, there's another one here. Don't know if that's exposed or not. Feels like it. Wow. Yeah, really sky high on that. Oh, here's another one. Wow. I'm glad I spotted these. I did not think to look for them. Now, this cord's pretty stiff, I think it's time for a new cord. Completely. I was thinking about repairing this, but it's got 3 strikes. It's got a big strike here too. Did I miss that one? Oh my gosh. I think we're going to replace the cord on that. Replacing the cord then gives me the opportunity to use a 3-prong plug. At the very least, that can force the plug into the outlet in a certain position, so you can't reverse it. It can only go in one way. Even if I don't utilize the ground prong in the equipment. And these guys, you should not do that. You should not bring the green wire from the ground prong and hook it up to the chassis here. Well, maybe you should. That's your choice. You got to think it through. But as I'm thinking about it now, I wouldn't want to do that myself. Of course, what am I planning on doing in my shop? I'm planning on running a common bus across all this kind of equipment, and then guess what I'm going to connect it to? I'm going to connect that common bus to the ground. I'll have to think about that a little more. Maybe I should introduce three wires and settle this whole thing down that way. You got to think about that a little bit. You might have to lift this off the chassis and insulate it, or come up with an alternative way of connecting the test leads. Okay, so we're going to measure the output here. Look, they've got these really hidden here. I'm going to get a test probe. Just go right on the capacitor. We'll go right across the capacitor here. We'll get a voltage reading. Hey, my voltmeters, they're all apart here on the bench. I have to use one of these crummy newfangled ones. Newfangled. volts DC 200. Now what about the cord? Yeah, considering what I saw on the other one. This guy's not bad, he's a little more flexible too. Looking where these line wires go. One goes right up in this corner here where you can get your finger under it pretty easy, and the other one is going right there where it's exposed on the top, so you can put your finger on it really easily. Make yourself aware. Across the capacitor. Not sure I got it there. Put the brakes on here. Hey, where's the brakes? Where'd the brakes go? There we go. Okay. Zero. What's going on? Did I not turn it on? Tubes don't look warmed up. Yeah, that's a little better. I can see the light here. I can see the light. I can see the light. $159 is what I'm seeing there upside down. Where'd it go? 160 volts. That's all. Yeah, I wasn't watching very carefully there, so I'm not exactly sure what happened there. So it's still got 160 volts on the 150 volt capacitor. It does. There. It says 150 volts DCW. Working voltage. Never quite understood what they really meant by that. Working voltage. Well, it's not too surprising if this guy is just shot. Hey, capacitor checker. Okay, so you see the capacitor checker there with the wires hooked up to it, and the wires just go back over across the yellow capacitor, which I checked first to make sure there was no charge left in it, and it was a 0 for sure. Okay, so on the 25 volt setting that I now know is actually 50 volts. On the electrolytic setting, how leaky is it? Here's good. 150. Didn't quite open all the way on 150. No surprise there at all. So we will change this guy out. Not sure that test really helps out at all with the situation. Let's take this off. Go ahead and test the other one. Let's do that right away. I have the equipment here. Let's do it for comparison. This one's a little bit bigger. This is a 20. Testing these in circuit, they are in series with a diode and then a winding. So is this even a valid This is even a valid test. I guess if the diode is blocking, maybe it is. Maybe it isn't. It appears to be valid. With the same result there. Well, why not try to measure the capacitance? Give it a moment to discharge. Okay. So this is supposed to be, this one's a 20. 20 would be 10, 20. You can see the eye opens right around 20. I mean, there's a reason why I've been able to use these instruments. The capacitor is not completely dead. We'll check the other one. I'll go back and reconnect to the other one here. Dead, as in no capacitance, or open circuit, or short circuit. There's three ways these are. Okay, what happened there? What happened there? How did I you know, either nothing happened. I have a little nerve thing in my finger there that I think is a shock, or I got a shock off these right now. Something more to learn here. So I left the capacitor checker in checking mode. It's an AC voltage there. $60 volts. Is that because I left this unit switched the way I did? Let me switch it differently. So this is now ready to do the voltage test on the capacitor. There's nothing there. I will close this leakage button here. I should see 50 volts or so. Oh, this is AC. I should see 50 volts show up. Yep. 0 DC. Now switch the capacitor checker. Should have done this when I had it out on the bench, to checking. 60 volts. Let's try different settings here in the checking thing. This is resistance now. Oh, okay. So it looks like 20 volts AC. Really? 20 volts AC? So I must be using AC to do some of these tests, maybe. Okay, now how did I get a shock off that? 60 volts? What am I going to do? I'm going to grab them again and see if I can feel it? I don't know. You know what? I don't know what happened there. I'm not grounded to anything else. But I was being a little reckless carrying these two in my hand like that, so, you know, maybe. Here in the middle of me trying to avoid getting a shock, I get one. Pretty minor, though. I don't think that was anything important. I'd yell if it was really important. Now I've been so disturbed by all that. What am I doing? It's going to read the capacitance of this capacitor. That's what it was doing. I'm doing this in the circuit. I'm just not really sure. So we're expecting 16. 16 would be 50, 10, right in this range. There it is. So, you know, they're reading the proper capacitance. These are not opening all the way. Oh, look at this. Okay, so, this is the first time this has worked for me. So this is an adjustment where you are essentially, as I understand it, you are balancing the leakage resistance in the capacitor against something in the bridge circuit. And the result of doing this is you'll find out what the power factor is on your capacitor. And lower is better, higher is worse. So this one is measuring up at, you know what, I know what's happening. I restored this thing to proper operation, and now this is functioning properly. That's what's going on here. That's why I never got anywhere with it before. So, well, that's great. 15, power factor. Power factor is a big deal in power cable. Power cables are insulated. Very old power cables are insulated the same way these old paper capacitors are insulated. Yes, oil-soaked capacitor. Actually, oil-impregnated paper. Get the right word there. Paper. Oil-impregnated paper. What they actually mean by that? This is really surprising. I don't know about capacitors, but in a power cable, you have the big fat conductor, like that, and you want to insulate it so it won't touch, you know, anything outside, right? You got to mechanically protect this conductor from touching anything, and also create a distance, so you won't get a arc through from 5 or 10,000 volts. You wrap paper. I couldn't believe this when I started working in a power company, and I learned that these big power cables as big as your arm were insulated with paper. Paper? What? Yeah, oil impregnated paper. When they manufacture the paper and they're finished manufacturing the paper and they want to impregnate it with oil, they put the paper into a huge vessel. They extract all the air. The paper is made of tubes. The fibers are tubular. They extract all the air, and then they allow oil to come into the container, and without the air there, the oil will flow inside these fibers and get inside the fibers, impregnating the paper. That's why it's called impregnated. It's not just oil on top of paper. It's actually right inside these fibers. So the oil inside and the contaminants in the oil inside cannot travel through the paper, cannot move around in the cable. The oil is kind of trapped in these. Anyway, now what's the point of all that? Why did I go through that whole discussion? I don't know. I can't remember. I'm going to take these dangerous leads, turn off the machine, move them over there, and we'll get on with replacing these and sticking a 100 ohm resistor in series with it, and I think we'll be good to go then. So the first thing I'm doing is preparing the two capacitors with their 100 ohm current limiting resistors. I picked a couple of strong resistors there that can take any heat. There probably won't be any in here. It's all happened so fast on startup. I mean, think about it. Just bare naked capacitors in there originally, and well, we did have one diode fail. Maybe I should stop saying what I was about to say. There we go. This is going to sit in here, something like this. Negative lead prematurely here. Now, is this big capacitor going to get better voltage readings because of it? No, I don't think so. Unless there was some hum factor that was somehow affecting this meter. I don't think so. Gee, I watched a movie this morning before I came in here, part of a movie anyway, about Louis Pasteur, who we all know. Thank you, for pasteurized milk. We owe that man an awful lot more. An awful lot. I now realize he's one of the greatest humans on the planet in terms of what he did for all of us. And that is forcing the science around vaccinations. Forcing it into the heads of other, scientists of the day, who medical people now, who all just rejected what he was doing completely. And very interesting movie. A great man, for sure. In France, at the time, France had this terrible problem with oh God, what's the disease? Anthrax in its farm animals, and nobody understood, of course, initially what was going on. And it was Pasteur who figured out bacteria. He figured out bacteria. He figured out spores. He figured out the life cycle. And he did all this, I believe, if I got the movie right, during 10 years in which he had been rejected by the science community at that time in France. He'd been completely rejected because he had made some statements which I guess could not be proven, some other topic. For 10 years he was on the outs. During those 10 years, he, on his own, figured out anthrax, life cycle, bacteria, spores, and began to say, this was really radical thinking, right? Because he came forward and said, hey everybody, the reason we get sick is because there's something else alive that's invaded us. And this was a radical notion. What? Other things inside? What? Invisible things, sure. And according to the movie, it came down to a public demonstration which was intended to shut down Pasteur once and for all and rid France Scientific Society of a charlatan. They set up this experiment. I got more time to talk. They set up this experiment with, according to the movie, 100 sheep, 100 of them inoculated by Pasteur, and 50 of them inoculated, 50 of them not. And this other scientist had come forward and said he knew of a certain way to make animals sick, and it was to take, get this, it was to take the blood of a sick animal and inject it into the other animals. And so he stepped forward and said, I have a way of making animals sick for sure. Let's see if that vaccine will actually work. And then once we see that it doesn't work, Pasteur can be out of our hair forever. We'll never have to hear from him again. The crazy fool. And of course, they set this test up. And I think you know what happened. All 50 animals inoculated lived. So the scientific community, being the scientists that they are, they accepted the result. And Pasteur was a great man. And Pasteur, this is the interesting thing, he ran into another scientist, a researcher, an English researcher named Lister, Dr. Lister. Listerine. Listerine is named after Lister. Dr. Lister. There's something else too. Listeria. Bacteria we hear about these days. Listeria. I don't even know we're paying homage to people when we are. So the first one came out, had a leak in it. This one, it has a little thing happening there. Yeah, it's a great story, a human story about a man who has to withstand the completely unfair and unreasonable behavior of his fellow scientists. Of course, back then, it was a boys' club, right? Boys' club of scientists. And you don't dare stand up and tell everybody they're wrong. Hey, everybody in this room is wrong. You know where I learned that can happen? When I was in grade 9. grade 9, we're in this class, and the teacher asked this question, and I'm going to say her name, Martha Perry. Martha Perry, if you're watching this video, I'm talking about you. Martha Perry. For some reason, this girl was picked on by everybody, and not so much by me, but I just wasn't the kind of guy who would do that. But she put up her hand and gave an answer, and there was a big guffaw in the classroom. And of course, that was the dog whistle to all of us to reject what she had said. They had a clever teacher in that classroom. So he says, "Oh, okay," because he heard the dog whistle too. Okay. So how many people agree with Martha Perry? You know, not a single hand goes up. I think you know where I'm going with this story. Not a single hand goes up. How many people think it's then this? Pretty much all the other hands go up, including mine. Very proudly. Yeah, of course. And he says, "Well, you know what? She's right, you're all wrong." I was so stunned. Because it wasn't me being wrong. It was a room full of kids all being wrong together, and one being right and standing up. Well, she didn't really stand up to the... it was the teacher who took care of this. Receiving unfair... you know what I'm talking about. And I learned right then and there, it is possible for everyone to be wrong but one person. It happens. I've seen it happen. There's no reason why it can't happen. I remember being in a meeting when I was working professionally. Almost a dozen people in this room. And two people begin a conversation. And right away I'm thinking, well, wait a minute, the two of you are not talking about the same thing. You're talking about that, and that guy's talking about this. They went back and forth 4, 5, or 6 times. They were talking about entirely different things, and yet completely in agreement with each other, without realizing that the other was talking about something else. It was quite obvious to me. The other 10 people in the room just sat there and listened, and finally I spoke up and said, "Wait a minute, you two guys aren't even talking about the same thing." And everybody looked at me like, "What are you talking about?" And then after a couple of minutes they all realized, yes, you're right. We weren't actually even talking about the same thing, even though we were in agreement and kind of had no idea that that was happening. So that's another lesson there, that we can all be wrong together, and one lone guy like Louis Pasteur can stand for 10 years pushing ahead with what he himself believed, and in the end giving the world a gift, an immeasurable gift. One man. I love those kinds of stories. I'd like to be one of those guys, wouldn't you? I'd like to do something that saves the world from itself. I don't think fixing this little amplifier or little meter is going to do it. What about this floppy arrangement here? I don't like it. Why can't I just cut the wire off and tack that straight onto there? Can I leave the wire on and tack it straight onto there? It's not much better. Replace it with another diode. Do you think I can solder that on there? Wow, that's a lot of metal there. I don't think that's the strategy. I think another strategy is warranted. That strategy would be the foolish strategy of putting electrical tape onto it. Why does it smell like something's burning in my shop? Should I look in the mirror? Is there some smoke coming from my ears? Just must be the solder. So the reason I say this isn't the best solution is because this tape does not have a long life. Definitely not plugged in. Definitely not plugged in. to just make me feel a little better though, that we don't have this big hunk of metal exposed flopping around. That's terrible. Terrible tape job. Okay. Or I just added some fuel to the eventual fire that's going to come. Okay, what do we got? So we got the capacitor in, we got the ground to the ground. How do we know that's the ground? How do we know that's the ground? Because that's where the negative of the other capacitor was connected. The positive goes through the resistor over to this terminal. Honky dory. Let me check this one. So the positive going through the resistor, the positive wire, and the negative tied back there. We're ready for a test. They are ready. Okay, this guy first. What am I expecting to see? Nothing at all. Nothing special. Expecting to check for a full short because I did something stupid in the work. Checking to see if this resistor blows up. So we're gonna, oh, it's already on. So it's switched on to AC, which is fine. Put that there. We'll say, everyone, shield your eyes from the blast. Okay, so we're going to watch these lights. If they come on full, bad news there. And what else could happen? Well, we could pop this. I wouldn't see anything if it did pop. Last thing is the meter doesn't work now that I put this filter in with this resistor. Not very likely. Ready on the lights. Well, that's interesting. Okay, it didn't even light the dim lights, not even for a moment. So that tells you something about the inrush current. Tain't any. Everything's fine. Let's get a little voltmeter going here. Where's my voltmeter guy? Where'd he go? Here he is. DC voltage across the capacitor was 160 last time. This is a 160 rated capacitor. But I think it put a couple hundred. I don't think it would hurt it. There we go. And 158, just below the 160 rating of the capacitor. Voltage drop on the resistor. Lucky if we can even see it. To DC. Can't even see it. That's surprising. This goes to 200 millivolts. A little bit, something going on there. I think that's a hum. I think that's a hum voltage causing the meter to read like that. 2 volts AC. There's nothing here that's making me go, ooh. It's all good, it's all good. Power off. Plug out. Now this guy. Plug in. Keep an eye on our parts here. Switch it on to AC, same setting. Plug in. Watching the lights. Nada. Grabbing the voltmeter here. Reading across the capacitor. DC 200 volts. Positive here. Right on the capacitor itself, not on the resistor. Is my arm in the way? No. Careful. 167. It's slightly higher in this unit. 167 on a 160 capacitor. Doesn't make me panic. Voltage drop on the resistor DC. Okay. Tiny voltage. DC drop. Let me see there. 30 millivolts. kind of jumping around a bit. That's great. Now, this capacitor up here, where's his brother in this unit here? This is located right on the big switch thing. There he is. He's down in there. Same capacitor. Looking really good. Oh, there's a rating on it. I can read this one. 0.047. 0.047 microfarads. It's a 0.05. 0.05. Nothing special about this capacitor. Last thing, let's look in the schematic and see if we can find where 0.05 is. 0.05, roughly where is it? It's associated with all these resistors here. It has something to do with this too. There it is. 1600 volts. Is that why it is the way it is? Almost certainly. That's why that large capacitor for a 0.05 is there, because it's a high voltage capacitor. Looks to me to be in beautiful shape. You know, capacitors can deteriorate internally. They can come with enough of their own contamination and moisture inside them that over years and years and years they can deteriorate all on their own. Not very likely though. 0.02. So I'm pretty sure this is the one we're looking at, because that 1600 volt thing. It's a little one here. I didn't see any other tubular or paper. Yeah, there is one. There is one. There is one. It's a molded capacitor. 0.05 molded capacitor. Here. Get myself ready for tomorrow's work. So it's a white capacitor down in there. This powers off. Plugs out. There's a white capacitor down here. You can barely see it. Is there one of these over yonder? Or is that white one a replacement? Where is it? What's it associated with? It's associated with, it's right on the tube socket for this tube. I would put it over in here. Now I see some ceramic ones in there. That's probably what's in this unit. It could even be a replacement. Somebody stuck that in there to replace a ceramic. Maybe. Yeah, I don't see it any other place. So we should give some consideration to this. What was it doing? What was it doing? I think it's, well, you know what, I don't know what it is. 0.005, 0.005, 0.02, going to ground, and 0.02 over here. Well, I don't know which one it is. We'll worry about it on the next session. This is what's really in store for me. Oh, there's my neighbor shoveling away over there. This is where I'm heading next. Out here. I'll show you. I don't know if we can get the camera to look out. Yeah, it's a little hard to see. That's my driveway right in there. Buried under the snow. That's about 3 feet of snow here on my front yard. Actually, you can kind of see in the neighbor's yard what it's like. That's where I'm heading next. Okay, so I think we've done the first stage here. Part of it is cleaning up a couple of parts. A lot of it is me getting used to looking at this, getting comfortable with the schematic, and just getting comfortable with everything. I don't think we're going to do too much to this guy, much more than we've done already. Calibration is the key. I think calibration is what I should try. If it calibrates, it's done. I think that's kind of the way to do this. Thanks a lot for watching. See you on the next one.